Did you know? We have published an Etabs course with a complete 20-story building design. The course will include complete guide to Etabs, from basics to advanced level with a completion certificate. Check link in description of this video.
In this lecture, we will learn the design, analysis, and modeling of the masonry structure in Etabs. The download link for the report template for the design of masonry structure is given in description. So we'll be utilizing the UBC 97 or ACI 99 code for seismic loading service combinations of allowable stress design and FEMA 356 for stone masonry properties. The software to be utilized will be Etabs. As we all know that we are using the Etabs 2016, which is the most stable version of Etabs till the publishing date of this video. I am assuming fair condition masonry, that is 600 psi compressive strength. The reference is given. The modulus of elasticity of the masonry is also given and the reference is given. The masonry shear strength is 20 psi, again along with the reference from the FEMA 356 table. I am assuming a low strength stone masonry, and the modifiers will be incorporated for the concrete as 0.35 for moment of inertia of the walls. We will be taking the soil type as SD. The masonry shear and other parameters are also discussed in detail in that document. We will be starting with the importance factor for seismic loading. The building is confirmed to have emergency equipment or it doesn't have 500,000 occupants. So the importance factor will be 1. Seismic zone 3 soil type SD. So we are getting the seismic coefficients. You can also edit this report for your design code requirements. It's easily editable. However, the template is highly useful for the report format of the masonry structure design or analysis, and highly acceptable as I have utilized personally it in many projects. So I'll be defining the grids first. Let's take it as 20 feet in X and Y direction. Number of stories is 1 since it's a 1-story structure. I'll be adding the new material. Etabs has built-in masonry option and the FC we are to be using is 600 psi, but the minimum specified here is 1500 psi. So I'll be editing it to our material, that is 600 psi compressive strength. The density remains same. We'll be checking this property from the table calculated. 550 of the formula into 600, that is the compressive strength. We get a value of 132. Oh, 330 psi. Okay, and the Poisson's ratio is 0.25. As we'll be observing the stress in the material induced by the loading, so these properties are highly important even for linear static analysis. Let's modify the compressive strength property of the material, that is 600 psi pounds per square inch. And then click on OK. the compressive strength of the concrete. Since we will be using the band beams and the reinforced edges, it would not be right to call them as columns as they would be too slender and small sections. So I'll be calling them as reinforced edges of the wall or reinforced interlinks between the walls, as it may be required that we will be providing these reinforced corners or portions of the wall in midway of the wall. So let's define the wall section of the masonry. The masonry wall we are thinking to take is starting with 8 inches, as the block size is of 8 inches we'll be using in the project. Usually it is also specified that the thickness is to be taken by the architect. So I'll be using the 8 inches thick wall. So I'll be taking crack moment of inertia for the walls. Because the reinforcement provided in the walls will be just at the defined edges. We can also take the properties as layered, but it would be too complicated for the analysis. Rather, we'll stick to the simplicity and go with the simple wall with a uniform cross section. And then click on OK. Frame properties for the band beams to be defined is 8 inches by 12 inches. Let's go to define section properties and frame sections. Eight by 12 inches. And then the wall section now I'll be taking the reinforced edge of the wall. So I'll be taking the 3000 psi concrete for this particular area. If you are using hollow block, you can simply enter the compressive strength of the block, but I am using the concrete edges of 3000 psi, so I'll be using the compressive strength of the concrete. You can enter the corner bar information and the other information. Similarly, for the band beams, I am taking the compressive strength of the concrete, since the band beams are of reinforced concrete. I am specifying the number of bars since we have only corner bars, so edge bars are being set to 0. Actually, we have to rotate it, so make this one 12 and make this one as 8 inches. Now it seems fine. Oh, so we have 2 extra bars, so I'll be removing these bars. We already made the edge bar 0, but once we rotate the shape, it again resets the bar at the particular edges. And click on OK. Similarly, click on OK here and here. You can set the property modifiers for the beam here as per ACI code to incorporate the cracking of the moment of inertia. You can delete the steel sections which are not to be used, preloaded by Etabs, and click on OK. Now let's define the column section or the reinforced edge. The section size is 8 inches by 18 inches, reinforced with 2 number 3 bars. I don't think I can place 2 number 3 bars in section designer even, so I'll be placing 4 number 3 bars, as 2 number 3 bars would be too short for an 8 inches wall. I'll repeat again, if you are using the reinforced edge for the hollow block masonry, then you can take the material property as masonries only, but still I am using the concrete edges of the wall, so I'll be sticking to the concrete property. Now the moment of inertia for the edges or the column shaped member or the vertical reinforced member is 0.7. I'll click on reinforcement to be checked and then define the reinforcement. We are having a 6 inches thick slab. Let's modify the slab property. And the property modifiers for the slab. The property modifiers to incorporate the cracking of moment of inertia according to ACI code. And click on OK. You can use these modifiers and other properties as per the code you are using. However, the basic concept remains same. Let's start modeling the masonry structure. I am assigning the mesh to the shell objects, that is wall and slabs. It is preferred to use equal mesh sizes as the load transfer and the stress transfer and the force transfer occurs through the mesh sizes. So the mesh I'll be keeping is 2 feet for higher accuracy. The lower the mesh size, the accurate are the results and more analysis time required. But since our structure is very small, so we'll be using a 2 feet mesh size. So it won't take much time to perform the analysis. dead, live, snow, and super dead. Similarly, earthquake in X direction, that is seismic load. According to UBC 97, you can define the earthquake in any respective code. In a similar manner, you define it for reinforced concrete structure. Let's uncheck the Y directional forces and select SD, that is the soil type given to us, and seismic zone 3. The program. So the CT value for the masonry structure is 0.02 and the strength reduction factor is 4.5 to incorporate the ductility of the structure. These all parameters were defined as per UBC 97. You can incorporate these factors for your respective codes. As I selected UBC 97, so I'll be incorporating the parameters in UBC 97 format. So soil type SD and seismic zone 3, over strength factor 4.5, and click on OK, and OK from here to exit the menu. We have defined all the loads. Now it's time to apply the loads to the structure. Assign the rigid type diaphragm to the slab. So the diaphragm lies in the center as the structure is symmetric, so it means the modeling is done correctly. Assigning the live load to the roof, and similarly I'll be assigning the snow load and the finishes load. The super dead load for the finishes is 36 pounds per square feet. Similarly, the snow load is 20 psf. So meshing the wall as we previously assigned in 2 feet maximum size. To mesh the slab meshing so that the force transfer becomes accurate. I'll be defining the load combinations. Simply dead plus live. That is the service combination, and the other dead load is finishes load, and click on OK. And now copy the combination and make the earthquake combination. Since we are using we'll be checking the service stresses as per UBC 97, so we are making the service combinations, not ultimate combinations. UBC 97 utilized service combinations for allowable stress design method. The masonry structures are designed using allowable stress design method as per previous codes. You can define the combinations for your code. Now I'll be defining the same combination for the Y direction, since we have incorporated earthquake in X direction in load combinations till now. So I have opened UBC 97 code and the combinations are shown. Since the live load of the roof and the snow load are alternatives of each, but here in our case the values are both 20 psf. The live load for the roof is also 20 psf and the live load for the snow is also 20 psf, and in combinations they are repeating as. So our roof load and the snow load is 20 psf, that is equal value. So no need to repeat the combination for the snow load as we have already incorporated the same combination for the roof live load. It is a pure coincidence that our roof live load and snow load are same. So I'll just keep the things simple and work with the roof live load only, as the snow load is equal to the live load and the combinations for the snow load and live load are exactly the same as per UBC 97 allowable stress design method. If you are using a different code, then you'll have to see the provisions of the code and their combinations. There is no harm if I would have taken the snow load in along with the live load, but just to reduce the efforts and save time, as I know the results would be same, so I keep the things unchanged. Now let's perform the analysis on the structure. So if you see, the mesh size is exactly what I wanted. The wall and the slab meshes are exactly matching and the nodes are transferring the loads. Let's check the seismic base shear on the structure. The period and the weight utilized of the structure by Etabs, as we define the mass source for the dead loads only. Mass source include dead loads as per UBC 97, and if you want to incorporate live load, then the structure must be a little bit high rise. So I'll be editing this list for my project. This is a ready-made list and the link to download this document has been attached in description. It is a basic masonry structure design report template. You can easily edit these values for your structure and prepare a masonry structure design report in a professional manner. I personally use this report template in my own projects and clients really like it. So you can use the template for your projects as well. The link to download this report is given in description of the video. Okay, so I have incorporated the weight utilized of the structure and the base shear calculated by the software as per the code UBC 97. Now let's draw the openings in the walls. Actually, we should have drawn the openings in the walls and completed the model in a previous stage, but let's just try to do it, as I just have to see that the model we have done so far is right. And for demonstration purposes, the structural behavior will not change much as it's a masonry structure. So if we add openings along with the lintel and the spandrel and the tie beams along with the band beams, so the behavior of the structure will not change much. However, the stresses in the structure will reduce the more corner elements we add. So I am creating a doorway in the wall. Since the wall height is 10 feet and I need a 2 feet bend in the top, or a 2 feet masonry over the lintel of the opening. So I'll divide the beam into the model line into 5 segments, so that 10 feet becomes 5 segments of 2 feet. And now I can easily draw the lintel and break the slab from here. Now we have created the opening. Similarly, we need to create an opening for the window or the skylight. Similarly, I'll be dividing this line in a similar manner, as I need the sill level at 4 feet from the ground. So now I've made the window opening here. So after assigning the openings in the masonry structure, we will be checking the preliminary stresses in the structure. So I've made the base supports as fixed and save the model. Now I'll be assigning the corner elements of the walls, that is the reinforced concrete edges and the band beams, of course. So the band beam will come just beneath the slab, and it will perform as a bonding agent between the wall and the reinforced concrete slab, and it will form joint with the reinforced concrete edges of the wall, which I will be placing right now. So this is the reinforced concrete edge, which we defined just like a column. Right now we haven't added the internal partition wall in the structure. We will be checking the results of these stresses in the next part of this lecture, and the link to the next part of the lecture is given in description of this video. However, we can check the seismic base shear again and see if there is any much difference. and then we'll be adding the interior partition walls in the structure. As the spans according to the first modeling, the spans are quite large for a masonry structure. So there are large deformations in the slab and large force transfer from the slab to the walls. So definitely the stresses in the walls will be exceeding, which we will check in the next part. Similarly, we'll perform the checks for seismic drift, and you can download this report template. The link to download this template is given in description of the video. Alright, so let's define the load combination of the envelope and the earthquake drifts. Since we are using UBC 97, the drift is 0.7 into strength reduction factor times the elastic drift. The seismic base shear is elastic, so we have to increase it by 0.7 R times. You can use the drift criteria of your respective code. Now we'll have to click here, add story, maximum or average displacements, and check it with our code criteria. Since we are checking drift for earthquake load only, earthquake drift maximum and minimum. The drift limit as per UBC 97 is 2% or 2.5% because the time period is less than 0.7 seconds. So we are okay in X direction. Now let's check for the Y direction. In percentage, it is 0.36%, which is again less than 2.5%. So we are okay with the drift. In the next part of the video, we'll check the stresses in the wall. Check link in description for the next part of this lecture for the design of masonry structure.